So today we are going to be speaking about free radical mechanisms. Now, you should all have done this last year or the year prior, and normally it's the first topic that you cover in organic chemistry. Now, this subject, whilst covered in a good amount of detail at A level, there are a few misconceptions. So, for example, if I were to give you the reaction of CH4 plus Br2 to give CH3Br plus HBr, some people think that we are writing all the products. In fact, even if you were to think about the mechanism, we are writing the two most prevalent products. And hopefully, you all know by this point that here we have an initiation, propagation, and eventually termination. So initiation is to start. And here we will break a bromine bond to form two Br radicals. This bond breaks via a heterolytic fusion where each electron will go to different atoms. Hetero, different, lytic, breaking. So you're breaking it to go to do different atoms. And it's important to note that this arrow represents transfer of one electron. So anytime you see one arrowhead, it is the transfer of one electron. Now, if up to A level, this was an accepted mistake, this will not be the case with university. The arrows have to be perfect. Okay? They start from the bond and they go to the atom. They start from the bond and they go to the respective atom. Now, we are also forming a radical, and a radical is an unpaired electron. Now, radicals are highly reactive and they are agents of change. During previous talks in the UK, I used to say that radicals are like Jesus Christ. They can do miracles because a radical will break even the strongest of bonds. Okay? And this is one of the ways, in fact, how you can break a carbon-hydrogen bond, which is normally one of the strongest bonds available to a chemist. A carbon-hydrogen bond, especially when this is part of an alkane, okay, or an alkyl group. Because normally that bond never ever breaks. You require something massive. And radicals can do it. And radicals can do it with ease. Then you have propagation. So propagation, yes, Sen?
I could be remembering this wrong, Ma. Isn't it supposed to be a reversible arrow?
Now, all reactions that we're going to be doing here are reversibles. But for the initiation, the intent is the forward reaction. What you are doing is you are breaking with UV. So in fact, here I should have written UV. In fact, in termination, one of the reactions is Br dot plus Br dot to give Br2. I try to avoid the reversibility, and I will explain why in a few minutes. Okay? I will try to avoid the reversibility here. And I will explain why in a few minutes, okay? Stay with me if you don't
All right,
understand
thank
it.
you.
By past, ask me. Okay, I think by past I would have covered it.
Okay.
Okay? Now, then propagation is to start with a radical and end with a radical. Okay? Start and end with radicals. So you can have our radical reacting with methane. And as we said, radicals are one of the few things that can react with a carbon-hydrogen bond, especially at room temperature. And even here, we will break one bond and put the electrons on the carbon. And here you will get a methyl radical plus HBr. Apart from this, then, the methyl radical can react with a bromine to form CH3Br plus Br dot. Now, a lot of students in the past have asked me, if bromine reacts in the first step, why do I still have bromine that can react with CH3 radical? And the reason is this. When you initiate F radical substitution, only a small percentage of the bromine will dissociate into radicals. You don't give enough energy for all the bromine molecules to form bromine atoms. That is not what you want. What you want is to initiate the process, to start getting a few bromine radicals. And once you have 5, 10, 15, 20 bromine radicals, these can then react and propagate. You don't want to have too many initiators. What you want is a lot of propagation. The more propagation you have, the more products you've got. And remember, these are the products that you want, HBr and CH3Br. In fact, you can consider that the products in termination, even if you get the bromomethane, it's not what you want, because that will be killing off your reaction. Because of this, you just put a little bit of UV. Normally, you just switch it on and off, okay? In some cases, I remember I used to have every 5 minutes, it switches off for 1 second, and then it switches off, and see what happens. If there's propagation, the reaction will happen. Which means, even if you are forming Br radicals, okay, let's say you had 1,000 bromine and 1,000 methane. If you have 10 Br radicals, what will they meet? Will they meet another radical, or are they most likely to meet a Br2 or a CH4? They are most likely to meet one of the other molecules. Whether it's Br2 or CH4 doesn't matter, and they will react. Of course, there will be this reaction. But this will result in more Br2 plus bromine radical. So they are the same. So we don't consider it. But if it meets and clashes with CH4, okay, we will get the reaction we've mentioned in propagation. This is why, in my opinion, we should not write a reversible reaction, because it's more likely to meet a methane than it is to meet another bromine radical. And therefore, the reaction is one way only. It continues. Of course, in termination, we do write Br dot plus Br dot, because eventually these numbers will start dwindling down. Let's say you get to 100 CH4 and 100 Br2. At this point, the probability of two radicals meeting will increase drastically. Propagation is the longest step in this reaction. By a longest step, I don't mean it takes a long time for one bromine radical to react with a CH4. But if you were to consider the time frame of the reaction, initiation, a few milliseconds in the beginning. Propagation can take up to a few minutes. Termination, it could be a few seconds at the end. And once you hit termination, you cannot reverse the reaction. You have to start it once more. Okay, Anne?
Yes, thank you.
Okay. Then termination you can have the two bromine radicals reacting. You can have two methyl radicals reacting to form CH3, and we can have CH3 plus Br radicals reacting to form CH3Br. Now, even at this point, okay, even at this point, it's important, okay? It's important to note that whatever you have, okay, you are going to try and avoid these three reactions. These three reactions only happen at the end. In order to try and get as much of these three as possible, okay, you need to change the ratios of the reactants, okay, which then it wouldn't be 1:1. But considering if you have 1:1, at the end of the reaction, you will start seeing the formation of CH3. So the carbon-carbon bond, a new carbon-carbon bond is formed. And the formation of CH3 of ethane is actually delayed. Delayed because in the beginning, as I said, the methyl radical is more likely to meet a bromine than it is to meet another methyl radical. So therefore, it doesn't happen. At the end, when the amounts are reduced, this will be present. So in the past, I've had students who told me, sir, if I want to double the carbon chain, can I use free radical substitution? And the answer is no. And the answer is no. Now, any questions? I take the silence that you're either asleep or you truly have no questions. Hopefully it's not the former. Now, so let's say take a couple of minutes to write the expected products of this reaction. And this is something that I would like to discuss in a little bit more detail for the rest of the lesson, okay? Today, possibly we won't stay till 4. Maybe we'll finish in 25, 20 minutes, okay? But let's see. Let's try and see if we can have a reaction for this one. So I think that's enough time. Now, the product for this reaction, there are two possibilities. You have CH3, 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 Br, and CH2, Br, CH3, CH3. Now, who would like to try and figure out which one of these two products is going to be most likely?
I think it's the lower one.
Gabriel thinks it's the lower one. What about the others? تحسبوا. So are you in concordance with Gabriel? Are you not? Is there a lot of infighting between the students right now on Facebook? Come on, what do you think?
I think it's the lower one as well.
Lower one as well. So let's figure out and speak about the intermediate. What is formed, what radical is formed to form either the lower or the outer. Now, or the upper, sorry. When you have the upper one, you will have that radical being formed, where you have the lower one, you will have this radical being formed. Now, instinctively, all of you should realize that the upper one is going to be a lot more stable. A tertiary radical versus a primary, sorry, 1 second. Yes, versus a primary radical. Okay? Now, apart from this, there is another big factor. Where the radical reacts, it is a game of chance. So radicals are so reactive that they will react with pretty much anything. Okay? So our starting material has 10 hydrogens. So the radical has a 10% chance of reacting with any of the hydrogens. Okay? Which means that if we are just going to be speaking about probability, this should be 10%, and the other one should be 90%. But that is not what we expect. What we get. That is what we will get in this reaction. Even though by probability, there is a much bigger chance that we will get the primary radical, which is less stable than the tertiary radical, something else happens. And what happens is we get what we call a hydride shift. We get what we call a hydride shift. So what is a hydride shift? You have a radical over there, therefore you will have internal propagation. Okay, so you go from having a primary radical to having a tertiary radical. which is more stable. So because the tertiary radical is more stable, the proton will jump carbon. Okay, it's called what we call a hydride shift. Okay, the proton will jump carbon. So take some time to write that down. And if there are any questions, please ask. So any questions on this?
Sir, can you please re-explain how this works?
Yes, of course, Joseph. That's why I'm asking any questions, because this is a new concept, and today, if you get this, you are going to be on par to doing well in your exam. I'm saying this because a lot of the questions will incorporate hydride shifts. Maybe what we'll see later will be a methyl shift. Instead of a proton moving, you'll move a CH3. But please just make sure that you understand these. So, we have two radicals. So the two radicals are these two. Okay? Now, the radicals as such, their stability, a tertiary radical is going to be a lot higher than a primary radical. Therefore, this is more stable. Do we all agree that the one I just highlighted is more stable? Okay? And this is more stable since, we have hybridization, the topic we discussed last week. So hybridization, you'll have the hydrogens on the carbon sharing the orbital, the p orbital of the carbon in the middle. So now what we end up getting is a hydride shift. So on the middle carbon, there's a hydrogen. Without the need of anyone telling it, the structure knows that its best conformation, its most stability, is going to be achieved when it has a tertiary radical. So there is a proton shift. Now this in nature, okay, in the environment, happens all the time. Hydrogens shift from one place to another, even in aqueous solutions. So you end up moving the bond, the hydride. So the hydride ends up there. So let's see if we just copy it. Okay. So we are making a bond between those, and we are breaking that bond, right? Forming a radical on the carbon. So the end product would be okay, so it goes from there to there. Mela, the hydride shift is a shift of one proton. Okay, the hydride shift is a shift of one proton, and I'm going to write it down for you. When you need to move from one type of carbocation to another. It doesn't have to be from primary to secondary to tertiary. It just moves, okay? It happens. The energy here is not that high. And we'll be using these a lot more, including energy diagrams, when we actually get to do some reactions, okay? So let's speak. A hydride shift is the shift of one hydrogen atom to form a more stable carbocation or carbon predicate. In fact, last year, I gave them one particular question. I gave students this reaction. Okay, and they were meant to give me the product. Now, write the product for this reaction yourself. And we can discuss from there in a couple of minutes. Okay, so give me the product. I would highly recommend that you might want to draw the mechanism. Okay, I am going to try and revert back to what you know from A level, because that really helps. For me, reverting back to what you know from A level really helps. So here, the first step is to form the electrophile, where you have CH2, CH2, CH3, and you have the bromine, the first carbon, plus Al, Br3, or AlCl3. It will work with both, okay? Since you have the aluminum being electron deficient, it will take the electrons from the bromine, and that will form the electrophile. CH2, CH2, CH3, with a positive charge on the carbon. Now, this was the trick in this question. In fact, I believe that for most of you, you would write carbon, carbon, carbon. But the result in this question was expected to be addition on the second carbon. Why? Because when you have this type of structure, there must be, or there will be, a hydride shift. Why? Because the options that this molecule has is to either stay as it is as a primary carbocation, or else has a hydride shift and it forms a secondary carbocation, and secondary carbocations are more stable. So in the second semester, we'll be working quite a few of these. Where we will be looking for the hydride shifts. Okay? Where we will be looking for the hydride shifts. And these hydride shifts are amazing because they can give you a lot of byproducts. Okay? They can give you a lot of byproducts. So these hydride shifts are really, really amazing. Okay? And this is what we're going to be speaking about in the second semester. In the second semester, we're going to be speaking a lot about reactions. Okay? In fact, I would like to spend quite a few minutes on the syllabus so as to not to worry people, because if you look at the syllabus, we might seem like we haven't done much yet. Okay? But we're on track. I think normally we used to have 4 lessons, but in 1 semester this year, we have lessons over 2 semesters, so it takes a little bit less time for the lectures. Now, let me speak a little bit about the syllabus. So I will be stopping the recording here.